Afternoon, everyone. I'm John Leadbetter, as Sean said. What I'm going to do is we've got quite a few slides, so I'll go through pretty quickly. We are time constrained, something from there. So for those who aren't aware, VEGA is a German manufacturing instrumentation company. So one of our heavy industries is mining in Australia. We believe the future of mining is in two areas for us. One is instrumentation development, the other one is adaptation to IoT4. In regards to instrumentation, okay, radar level transmitters have been on the market now a number of years. What we've done now is develop the 80 gigahertz model, so thing from there, which is our latest generation of liquid and solid radar level transmitters. These are the sort of things that we picked up in the past that were sort of not faults but challenges. So we looked at all of these particular feedbacks and said, right, we need to develop something that's going to overcome some of these obstacles. So, principle of radar, as your frequency goes up, your actual antenna size comes down. The natural outcome from there is you end up with a narrower, more focused beam angle. So traditionally in 26 gigahertz, you had a fitting of 1.5 inch, or DN50, you ended up with a 20 or 15 degree beam angle. Now that we're bringing the actual antenna down to a 3/4 inch, you actually end up with a 14 degree beam angle. The larger you make that process connection or antenna, the narrower your beam. So therefore you're able to get around a lot of obstacles, such as agitators inside vessels. You're actually able now to focus on your real level rather than picking up the echoes from the agitators. So if you look at a live example here from a crushing circuit, traditionally on the left was the 26 gigahertz model that had an 8 degree beam angle, had problems with picking up interference from the chambers, from there giving false readings and giving a slow response. On the right, we developed the 80 gigahertz, narrow beam angle, able to focus down the throat, giving you much more reliable signal, faster response. So traditionally we had 96 decibels of dynamic range or energy from the system itself. With the development of our 80 gigahertz, you've now increased that by 200 times, or 24 decibels. So we're getting a much stronger signal back, so when we've got a lower or less conductive product, we're actually getting a better return of signal. So traditionally in an application for 26 gigahertz, you would send down your transmission and you would pick up off low dielectric materials a very small echo. You change that over now to the higher range unit, send down your signal, and you're getting a much higher signal return, so therefore you're getting a much stronger, more reliable signal from your materials. Live example there, looking at a low dielectric material. The one above is our old 26 gigahertz, the one below is our 80. As you can see down there at the 25 metre mark, we're actually able to pick up that material. So that could be a lime silo, could be a low dielectric material. Again, with 26 gigahertz, build up inside the vessel itself, that's inside the beam angle, it's going to see that build up. Those build-ups can create false echoes, which means you get false readings. And the more build-up you have, the worse it gets. As you shift over to the narrower beams, you're getting a much stronger signal. You're not seeing the sides of the vessels, you're not picking up any build-up. One signal, one return. In comparison there. Build up, as in this, showing here on a bitumen tank, where you've got bitumen on the face. You're not able to see that bitumen, therefore you're not getting a reflection from it or blocking the signals. We don't control how people install the units, but in these cases here, they're installed in large standoffs. So I think from there, traditionally what would happen in these sort of areas is that you'd end up with a lot of ringing inside that tube before it actually came down and read the real level. Again, you've got so many different zones that it's focusing on, it ends up losing the signal. Change it over to the 80 gigahertz frequency. We're not seeing anything inside the standoffs, and all the echo that we're getting is the one echo from the material itself, much stronger, much more reliable. $700mm socket here, one single echo coming back, no interference. Lock-off valves, again the same problem, is that you're going to get a lot of ringing inside the valve stems themselves. From there, creating really a situation of you don't even know which is the real echo anymore. Again, by going through and changing over to a high frequency, you're able to get around those issues. You're not picking up those ringing echoes. You've got a much more reliable signal coming back, as in the example there. Moving into another part is differential pressure. In differential pressure, we again looked at feedback, and we're able to now give a much more sort of more precise type of instrument now. Bluetooth technology is something that the future is holding. We've been doing it now for about 2 years. Communication through smartphones, iPads, tablets. From there, single chamber EXD, SIL approvals, and you get your measured value and an event memory, in other words, asset management. What you're also getting out of there is you're getting 2 outputs, one for your differential pressure and one for your static pressure. So you can have them as 2 separate outputs, faster response times, improvement to accuracies. So again, development of a technology by getting more out of the technology from there. Bluetooth, as I said, Bluetooth devices now, so things from there across the transmitters. In an EXD environment, you're actually able to operate this through the glass lid, where you can actually do the programming with a magnetic pen. So therefore you don't require to go in there with and break the integrity of the EX area. It can be done by a laptop, communication, Bluetooth 4, communicating directly to the instrument, roughly about 20 to 25 metre range. It can be done through a smartphone or a tablet. The apps are downloadable from the app stores, from there they're free of charge, and you just communicate through, and away you go. Industry 4. Okay, traditionally what we've looked at with Industry 4 is there been the 4 stages of industry development from 1784 right through to today, from there. So we've looked at the fact that you've got all your different levels of communication and management. What we've had to do here is look at the fact that everybody has access to the same information. From there, so through a cloud service. So traditionally it's been done through HART, Profibus, Bluetooth communications from there. In the signal conditioning through Ethernet or Modbus. Future which we're under development now is for Profinet and OPC UA. So these are currently under development from there. If we look at mobile communication through the networks, okay, GSM, GPRS are all available from there, or through the router systems, Wi-Fi, Internet, Ethernet, sorry, Bluetooth. Again, under development, and again, heading towards 5G networks. So traditionally with Bluetooth communication, it's a case of accessing the information so that you can keep maintenance, stability, everything like that with your instrumentation. So this is a communication, not an output, using this type of system. The development now through a Bluetooth gateway where that information can be uploaded to the cloud, and then you can access that information from the cloud. It can be displayed remotely. So it is a case of developing Bluetooth now more as a communication path, as an output path, as well as a communication path from there. Wi-Fi networks, hardwired networks all go up into the cloud, and that information can be accessed remotely. Okay, again with Bluetooth, up through the gateway into the VEGA cloud, and that can be accessed by third-party systems. So again, development towards third-party access through SAP, OPC UA, where you're able to access your own information from there and control your network and your instrumentation. Okay, so that's briefly it. We're over on stand 17. I know it was a brief overview. If anybody wants to come across and actually see the units demonstrated in those types of applications or the communications, by all means, feel free. Any questions? Nice. Thank you.